This video lecture will talk about weighted least square, which is one extension of the linear least square. As we see previously that the problem of linear least square is to solve beta from minimizing the two norm of y minus x beta. Weighted least square generalize the problem of linear least square in the sense that given positive definite matrix W, right, you use this matrix W as a weighting matrix in the least square cost objective. That's the formulation. And when W is positive definite matrix, you can always factorize it as L transpose L. You can use any kind of factorization, Cholesky, eigenvalue decomposition, and there are many ways. So suppose you have this factor, sometimes we call L the square root. From that factor, so you can write W. So you can write weighted least square in this form, and then it will also equivalent. It is also equivalent to minimizing L times x beta minus y square. So the only thing that extends from the linear least square is that you put some weighted matrix here in the residual. All right. Residual is the error between x beta and y. All right. So when you have L multiply on the residual, now remember the residual is a vector. Suppose it has m rows. Okay. So if you put L, of course, it means that you put different weights on the samples I of the residuals. For example, in a very special case, if L is diagonal, right? L is a factor of the weighting matrix W. If it turns out that W is diagonal, you can, the factor L is diagonal. So can you multiply these L and E? Kanatat, can you multiply it? Kanatat is not here. Sitipak.
L1 E1.
L1 E1.
L2 E2.
Yes.
And
okay.
so on to LM EM.
Right. Okay. So it means that you put different weights on the residuals I, and of course, think about when W is diagonal. Okay. For example, W is 1, 10, 2, right? Of course, the factor L will be square root of them. So the factor L must be positive. Okay. When you have the least square sense will be the sum. You minimize the sum of the residuals, right? So it's going to be LK EK square. Okay. So when you can take a look in this way that, okay, I usually for linear least square sense, I minimize the sum of the residual square, but for weighted least square, I put different weights. So if LK, in this example, okay, if the sample 2, right, I put W as 100. Okay, so there's gonna be a higher weight on the second sample. So if I put more weight on the second sample, it means that I want the residual on the second samples to be penalized more, and it should be less. Like I put so much penalty on the second sample. So we will illustrate with the experiment in the next slide. So for now, okay, let's see how to solve weighted least square. So when you take a look at this cost objective, all right, if you take the gradient respect to beta, all right, again, This is a function quadratic composite with f phi. So when you take the gradient, first you will get w x beta minus y, and then you take the chain rule, take the gradient respect to beta, you're gonna get x transpose here. All right. That's the zero gradient condition because weighted least square is again yet another unconstrained problem. And then when you set it to 0, that is the normal equation for weighted least square. And then, of course, just like the same way, these turns out to be a square system. Okay, it's like AX equals B, where your A is this matrix. Okay, and of course, if we can show, just like the linear least square sense, that if A is full rank, you can show that X transpose WX is positive definite matrix, given that W is positive. All right. So when X transpose WX is positive, it is invertible. The weighted least square solution is given by this, just inverse this term. All right. So you see that the modification of the weighted least square is just that, okay, you have W, the weighting matrix appears in the formula, and it also reduces to linear least square when W equals what? The top? The weighted least square reduces to linear least square, the ordinary one, when W equals the top.
What is it? P equal to P.
What is P?
Orthogonal matrix.
No, orthogonal. This is a more general case, right? The weighted least square. The question is, weighted least squares reduces to ordinary least square when W equals
I,
right? When W equals I, and you can also see just from both the formulation and also the solution. Okay. When W equals I, beta hat is just the expression we have seen before. Okay. We can also show that for linear least square from the previous lecture, we also give this result that the vector y hat, which is x beta hat, that we can take a look at it as, you know, p times y. This is called the projected vector y. We can show that this y hat or py is a projected of y onto the range space of x. It's called orthogonal because it's perpendicular to all the vectors in the range of x. For weighted least square, we also have this similar meaning. X times beta WLS, all right, which is our y hat in this sense. This y hat is also orthogonal projection on the range of x as well, but when the concept of orthogonality is applied, it is used with respect to a new inner product space, which means traditionally when you say x is orthogonal to y, all right, mathematically it is that x transpose y equals 0. Okay, for weighted least square sense, we have the results that projected vector y hat, all right, is orthogonal to all the vectors in the range of x, but the concept of you know, being orthogonal is generalized in an inner product term that it is the inner product in the new one, which means y hat transpose w times z equals 0 for all z in the range space of x. This is the new inner product. that is associated with W, with the matrix W. Okay. Now let's take a look at how we can apply the weighted least square formulation in practice. So suppose in our problem you want to fit data points in the blue dots, okay? But it happens that some of your data samples are clearly they are outliers. Somehow with the sensor failure and with something with a sensor that the observed values are kind of out of range. You guess that this is not regular. Then if you use the linear least square, fit that is given by the red line. Of course, the concept of the linear least square, you try to minimize, right, the sum square of the error, and you take into account all the errors from all samples equally. And that's why the straight line given by the linear least square, it tilts a bit. It's tilted toward some of the outliers here. Now, let's take a look at the weighted least square. Let's say for now that W is a diagonal matrix. Okay, you have suppose you have n data points, right? And clearly the outlier occur at the sample 3, sample 9, sample 10. All right. So when you take a look at this and you will say, okay, I think that these samples are outliers. So it means that I should not rely on these measurements much. Okay, so these data points should not be taken into account much when I perform the estimation. So I intend to use less weight on these samples. Okay, so for example, for W1, W2, for other weights, I may use 1, but for W3, W9, W10, maybe I use 10 to the minus 3. Okay, so I would like to penalize less because I don't care much about how the fitting, I don't care much about the residuals occur from these 3 outliers. So when I do so, when I fit, I will get these dashed line given by the WLS. You see that the straight line will try to lie between normal samples. So it doesn't tend to adapt to the outliers. So this is one application of the weighted least square. So this formulation can be more robust method, robust to outliers than the linear least square. The solution can be solved in the same way. I mean the same technique because if you see this expression, it basically means that you can just use the backslash, the left divided command in MATLAB. Okay, but also weighted least square must have a command in computer language as well, but I haven't checked. So, but I think there is. Okay. All right, that would be the weighted least square. I would like to break this short video a little bit so that we can move on to another one.